Imagine you're trying to organize a massive cluttered house, like just a ton of stuff everywhere.
Oh, yeah, we've all been there.
Right. And your intuition probably tells you that the absolute best way to optimize the space is to, take every single item from every single room, tear down all the interior walls, and just dump your possessions into one giant pile in the front yard.
Sounds chaotic.
It is. But essentially, you're flattening the house. The logic is that, well, once you can see everything at a glance, like the big picture, you can finally sort it perfectly, right?
Right, that's the standard assumption.
But today, we're looking at a piece of research that proves doing exactly that,
Mm.
that will leave you completely paralyzed,
Mm.
just standing in a mountain of junk.
What's fascinating here is that we actually have a rigorous mathematical way to test that exact front yard assumption.
Oh, absolutely.
Yeah, we're unpacking a brilliant 2026 case study by a researcher who goes by the handle at Luck036.
At Luck 036.
Exactly. And the paper is titled Yosys Flatten Mode, a LDS hardware synthesis case study.
Which is quite a mouthful.
It really is.
Yeah.
But it basically measures what happens when you tell a sophisticated hardware synthesis tool to look at an entire computer chip design all at once.
Instead of like forcing it to look at manageable compartmentalized chunks.
Or it tests that core assumption.
And the results completely shatter that intuitive big picture logic. I mean, they really do. And that is the mission of our deep dive today.
Yes.
We're going to explore this case study, look at some mind-bending hardware generators, and find out why flattening a design, giving an algorithm total unrestricted visibility, actually results in a significantly worse outcome for the final hardware.
Yeah, to really appreciate the scale of this failure, we first need to understand the immense complexity of the house we're trying to build here.
Right, it's not a small house.
No, not at all. We aren't just cobbling together a simple digital clock.
Yeah.
The target design in this study involves these mathematically intense 3D and 4D shape generators.
Right, and reading through the source material, I mean, I completely nerded out over the math they were using to generate these shapes.
Yeah, it's pretty incredible stuff.
It really is. They are building modules called Sphere 2.3 and Sphere 3.723.
Which sound like coordinates themselves.
Yeah, they do. But they are designed to plot points on three-dimensional and four-dimensional unit spheres.
Right.
But the trick is, if you are plotting points on a sphere, you don't want them randomly clumping together in one hemisphere and leaving these massive empty gaps on the other.
No, that would ruin the geometry.
Exactly. You need them evenly distributed.
Which requires specialized mathematical sequences. The hardware generates these coordinates using something called van der Korpet or VDC base sequences.
VDC, right?
Yeah, it's a type of low discrepancy sequence specifically designed to avoid those exact clumping issues you mentioned.
So for the 3D sphere, the hardware uses a combination of base 2 and base 3 sequences, right?
Correct.
And then for the 4D sphere, it just throws a base 7 sequence into the mix.
It gets very complicated very fast.
Yeah. But generating those sequences is really only half the battle, isn't it? Because then the hardware actually has to calculate the physical coordinates on the sphere.
Exactly, and that brings in the heavy computational lifting. To find those coordinates, the hardware uses quartic algorithms to compute the sine and cosine values.
Okay.
Yeah, quartic is essentially a method for calculating trigonometric functions using only basic addition, subtraction, bit shifting.
And lookup tables, right?
And lookup tables, yes, it's brilliant. But in hardware terms, it means the logic being generated is incredibly dense.
Oh, I bet.
You have these VDC sequences feeding into lookup tables, which then feed into quartic instances, which feed into complex multipliers.
It is a massive, highly intertwined piece of digital machinery.
Very intertwined.
And to translate this pure math into actual physical silicon logic gates, the researcher relies on a tool chain called the Yosys synthesis flow.
Right. That's our builder in this scenario.
Okay.
The setup for the study requires comparing two distinct flows, to ensure a perfect apples-to-apples comparison.
Makes sense.
Both flows start with the same initial core synthesis step. But the divergence happens right before handing the design over to the logic mapping tool, a program called ABC.
ABC. And that has the critical job of actually assigning the physical logic gates. Right?
Precisely. That's its whole purpose.
So one flow leaves the design neatly categorized in its hierarchical modules, basically the rooms of our house analogy.
Right.
And the other flow injects a flatten command, stripping away all those module boundaries and just feeding the ABC mapper the entire design as one massive block.
The front yard.
The front yard, exactly.
Yeah.
Wait, okay, let's unpack this because before we even get to the results of that comparison, there's a detail in the study notes that I found both hilarious and deeply frustrating.
Oh, you mean the bug?
Yes. Before the researcher could even run this apples to apples experiment, the entire toolchain collapsed due to a fundamental bug.
Ah, yes, the issue with the foundation library.
Right. They were using a foundational file called tutorialtech.lib to define the logic gates for the system.
Standard procedure.
Yeah, but this file was completely broken. It was literally missing a basic inverter, a NOT gate.
Which is, pretty problematic.
And it was also missing BUF, or buffer, cells. Like when they tried to run the ABC mapping tool, it crashed and threw an error saying it couldn't find an inverter gate.
It's hard to synthesize logic without a NOT gate.
I mean, think about the irony here. You are trying to optimize four-dimensional mathematical coordinate generators, and the foundational software doesn't know what a NOT gate is.
It's incredible.
It's like trying to write a complex philosophical novel, only to discover your keyboard doesn't have the letter E.
That's actually a great way to put it. It is a stark, almost comical reminder that even the most advanced algorithmic processes are entirely dependent on their absolute lowest level definitions.
Yeah, totally.
The researcher actually had to explicitly patch that library file manually to include the NOT T and BUF cells before the experiment could even begin.
Which sounds tedious.
Very. Now, real-world commercial process design kits wouldn't have this specific omission, but in this tutorial library, it was a hard blocker.
But, once that duct tape was applied and the library was patched, the stage was set. We have our complex 4D sphere generator, and we're ready to find out what happens when we unleash the ABC tool on the Flatten design.
Right. Let's look at how the researcher framed the scientific setup.
Okay.
They established two hypotheses. The null hypothesis assumed that flattening the design would have absolutely zero effect on the final cell count.
Okay, so no change.
Exactly. And the alternative hypothesis, the one that logic dictates should be true, assumed that flattening would reduce the final cell count.
And that alternative hypothesis sounds incredibly airtight, doesn't it?
It really does.
I mean, the reasoning is that if the ABC tool can finally see across all the artificial module boundaries, it should be able to spot redundancies that were previously hidden, cut them out, and create a tighter, smaller, more efficient design.
That's the exact theory. The test subject chosen to prove this was the Sphere 332 module.
Okay.
To give you a sense of scale, this design begins as a 66,511 cell structure, broken down into 7 distinct submodules.
Wow, so over 66,000 cells.
Yeah. You have your VDC modules, your Cordic instances, and your multipliers all interacting.
So we let the ABC mapper run the hierarchical flow first, optimizing the submodules independently.
Right. Room by room.
Room by room. And looking at the data table from the study, it finishes with a final design requiring 153,154 cells.
Okay.
Then they run the flat flow, feeding the algorithm the entire 66,000 cell big picture all at once. And here's the twist that shocked me. Both hypotheses were dead wrong.
Both of them.
Yeah. The flat run ballooned to 159,111 cells.
Giving the algorithm total visibility across the entire design actually made it demonstrably less efficient.
Here's where it gets really interesting.
Yeah.
That is an increase of 5,957 cells.
A huge jump.
Yeah. The hardware got 3.9% bigger just because we removed the boundaries. I am genuinely struggling to wrap my head around this. How does giving a highly intelligent resource optimizing algorithm more information result in a worse outcome?
Well, to understand why the hardware expanded by nearly 6,000 cells, we can't just look at the final tally.
No.
No, we have to perform a gate autopsy. We need to forensically break down exactly which gates were added and subtracted when those boundaries were removed. The numbers demand an explanation.
Well, looking at the breakdown, one piece, actually does make sense to me.
Which one?
The flat design subtracted 31 buffer cells.
Right, which is the immediate mechanical result of removing a boundary.
Okay.
In a hierarchical design, you need buffers at the output ports of your modules to carry the signal cleanly across the border to the next module.
Like a messenger between rooms.
Exactly. When you flatten design and remove the borders, those boundary buffers are no longer physically necessary, so the mapper eliminates them.
I buy that. That's logical.
Yeah.
But staring at the rest of this data, the logic just completely falls apart for me.
How so?
The flat design added 1,478 multiplexers, MUX gates.
Yeah, that's a lot.
Now, MUXs are essentially railway switches, right?
Yeah.
They route different signals to a single output. Why would tearing down walls create a massive new need for 1,500 new traffic routing switches?
It happens because flattening exposes all the select logic to the ABC mapper at the exact same time.
Oh, I see.
Yeah. In a compartmentalized hierarchical setup, the enable and reset logic is handled locally, quietly, within its own module.
Right.
But when you flatten the entire chip, the mapper is suddenly forced to merge all of this enable and reset logic across a massive unstructured expanse.
Wow.
To combine all those previously isolated signals, it has to build that massive new rail yard of MUX, as you mentioned.
Okay, so it's basically overcompensating for the sudden lack of local management.
Precisely.
But that still doesn't explain the biggest mystery in this autopsy. The flat design added 1,500 new A&D gates.
Yeah.
And staggeringly, it added 2,845 new NOT gates. Nearly 3,000 basic inverters added to the pile. Why the massive explosion in primitive gates?
If we connect this to the bigger picture, it really comes down to how the ABC tool's brain mechanically functions under pressure.
Okay, tell me about its brain.
ABC uses something called a greedy covering algorithm. It is an incredibly smart piece of software, but greedy means it makes the optimal local choice at each step, hoping it leads to a global optimum.
Right.
When ABC works hierarchically, it's looking at modules that range from a very manageable 245 cells up to about 45,000 cells.
Okay, so smaller chunks.
Exactly. In those smaller, well-structured logic cones, the algorithm has the processing power and the focus to scan the network and find highly efficient, complex gate matches.
Wait, what do you mean by complex gate matches? Are we talking about combining basic A&D and OR setups?
Much more dense than that. The library contains prepackaged clusters of logic macros known as AOI, OAI, or XNOR gates.
Oh?
These complex macros can do the job of 4 or 5 basic primitives in a single, highly optimized unit.
Wow.
Crucially, these complex gates often absorb inversions. They handle the NOT operations internally without needing a separate, standalone NOT gate.
Ah. So when the algorithm is packing the design room by room, module by module, it has the focus to find these clever space-saving macros.
Yes. But what happens when you flatten the design?
Everything is in the front yard.
Exactly. You strip away those manageable modules and present the greedy algorithm with a single, massive 159,000 cell block of unstructured logic, a giant soup.
And the algorithm's brain just blue screens.
Effectively, yes. The search space for finding those clever, complex gate matches becomes astronomically large.
Because it's looking at everything at once.
Right. The computational complexity explodes. The greedy algorithm simply cannot compute the optimal matches across that much surface area. It panics.
It panics.
Because it can't quickly find the AOI and XOR matches, it abandons them entirely. It takes shortcuts.
So it defaults to the lowest common denominator.
Exactly. It decomposes this massive blob into the simplest, bulkiest primitives available. Basic A&D gates, MUXs, and standalone NOT gates.
Oh, wow.
That is precisely why your NOT gate count skyrocketed by nearly 3,000. The tool lost the ability to absorb those inversions inside complex macros, so it had to stamp out thousands of individual NOT gates just to make the math work.
I love this because it vastly improves our original house packing analogy.
How so?
Let's say it's like packing a trunk for a long trip. If I pack it bag by bag, hierarchically, my brain only has to solve a 20-item puzzle at any given time range.
Right.
I can find the perfect combination where the rolled-up socks fit perfectly inside the shoes. That's your complex macro gate. I'm efficiently absorbing one item into another.
A perfect visualization.
But if I dump 5,000 items in the driveway all at once and tell my brain to pack the trunk, my own greedy algorithm crashes.
Yes, it does.
I stop looking for clever combinations. A shoe is no longer next to a sock. It's buried under a pile of shirts and a toothbrush. Right. I panic, I stop trying to nest things together, and I just start shoving individual shirts and individual shoes into the trunk one by one. And because I'm using primitive packing methods, I end up needing 3.9% more trunk space.
That is exactly the mechanical failure of a greedy algorithm scaling past its limits. The complex, space-saving solutions literally disappear in flat mode because the algorithm cannot see the forest for the trees.
It's just trying to survive.
Exactly. It breaks everything down into bulky primitives just to survive the computational load.
Which brings up a glaring contradiction, I think.
Okay, what's that?
If flattening a complex design ruins the optimization, balloons the cell count, breaks the algorithm's ability to use complex gates, and forces it to build a messy rail yard of MUXs, why does the flatten command even exist in Yosys?
That is a very fair question.
Like, why would any hardware engineer ever use it?
That is a critical question because flattening isn't inherently bad, it just serves a highly specialized master. There are very specific pragmatic scenarios where breaking those boundaries is absolutely non negotiable.
Give me an example.
For instance, consider formal verification tools.
Okay.
These are software programs that mathematically prove a chip's logic won't fail. Many of these tools strictly require a single module netlist to run their proofs.
Oh, I see.
If you don't flatten the design, the verification tool simply throws an error and refuses to run.
Okay, so in that case, it's an interoperability hostage situation.
Yeah.
You have to flatten it just to make the next piece of software in your tool chain happy, even if it costs you some physical efficiency.
Precisely. Similarly, some older place and route or PNR tools, which physically map where the silicon goes on the chip, will flat out reject hierarchical designs.
So again, you have no choice.
Right, you flatten them because you have no other choice.
Mm.
But beyond compatibility, there are a couple of specific architectural cases where flattening actually does help logic optimization.
Let's talk about those because I want to know when the big picture approach actually works.
Flattening can genuinely reduce cell count if your design features cross-boundary constant propagation.
Okay, break that down for me.
Imagine you have a submodule designed to accept a variable input,
Okay.
but in your specific overall design, you've hardwired that input to always be a constant zero.
Got it.
If you maintain the strict boundaries, the synthesizer might blindly waste cells building the logic to handle a variable that will never actually change.
Because it can't see outside its own room.
Exactly. Flattening allows the tool to see that constant zero across the boundary, realize the logic is fixed, and strip out the unnecessary gates.
That makes total sense. It lets the tool trim the fat that's hiding behind the walls.
The other optimization scenario is dead logic elimination.
Dead logic.
Yeah. If a parent module is designed to completely ignore certain outputs coming from a submodule, flattening allows the tool to follow the wire, realize those outputs go straight into a brick wall, and delete the underlying logic that generates them.
But looking back at the 2026 study, it becomes painfully clear why those exceptions didn't apply to our 40 sphere generator.
Very clear.
In these mathematically dense LDS hardware designs, every single signal was a variable. There were no hardwired constant inputs.
Nope.
And every single coordinate output generated by the submodules was strictly consumed by the parent module. There were no dead wires.
Exactly. The boundaries were already incredibly tight by design.
No fat to trim.
Absolutely no fat for the flat mode to trim across the borders.
Ah.
All the flatten command managed to do was overwhelm the greedy algorithm with a massive search space.
So what does this all mean when we step back from the A&D gates and the VDC sequences? What is the ultimate takeaway for you from this case study?
The core insight here completely flips how we should view hierarchy in systems. We tend to view module boundaries as artificial obstacles to optimization.
Like they're getting in the way.
Right. But this study proves they're actually essential structural aids for the mapper. Hierarchy acts as a cognitive guide for the algorithm, breaking an impossible, computationally infinite problem into tractable, bite-sized pieces.
Right, the room-by-room packing.
Exactly. It gives the algorithms clear, manageable targets so they can actually utilize complex, highly efficient solutions.
And I think it also screams a very loud warning to engineers, which is measure, do not assume.
Oh, absolutely.
The researcher assumed flattening would help. Our basic human intuition says the big picture is always better, but when they actually ran the data, it proved the exact opposite.
You really have to test your own specific flows.
Because the quality of your library, the physical size of your modules, and the tightness of your boundaries change the math completely.
That is the definitive engineering takeaway. Assumptions are the enemy of true optimization.
It really is an incredible deep dive into how algorithms process the world. We just assume computers have infinite capacity and want all the data all the time.
Yeah.
But even silicon brains need things categorized into manageable chapters to do their best work. Constraints, like module boundaries, aren't limitations holding the system back. They are the necessary scaffolding that allows for high-level performance.
This raises an important question, one that extends far beyond the realm of hardware synthesis and logic gates.
Oh, where are we going with this?
Well, if a highly logical, mathematically rigorous computer algorithm gets completely overwhelmed and performs significantly worse when it is stripped of its hierarchical boundaries and forced to process a massive flat system,
Yeah.
how does this apply to our human organizations?
Oh, wow. That is a fascinating
Well,
parallel.
we see this trend constantly. There is a massive push to flatten corporate structures, to remove middle management, to eliminate departmental boundaries so that everyone can supposedly see the big picture and collaborate directly.
Right, the open plan office of management.
Exactly. Or consider how we try to process massive amounts of raw data in a single dashboard without categorizing it first.
Overwhelming.
When we do this, are we actually deceiving ourselves into thinking we are optimizing our workflows? Are we, in reality, just degrading our collective efficiency by overwhelming our own human, greedy covering algorithms?
That is a brilliant and honestly slightly terrifying point.
It makes you think.
It really does. Maybe there's a profound systemic reason we put our clothes in distinct drawers instead of just leaving them in a massive flat pile in the front yard.
Exactly.
Sometimes a little bit of compartmentalization and structural boundary is exactly what we need to keep from panicking and just shoving basic primitives into the trunk.
Well said.
We are going to leave you with that idea to chew on. Look at the structures in your own life. Are you helping your brain out, or are you forcing it to operate in flat mode? Thanks for joining us, and we'll catch you on the next deep dive.